Hello, this is Matthew Dubuque, and I'm a graduate student at Georgia Tech. Today I will do a presentation on a paper labeled "clkscrew Exposing the Perils of Security-Oblivious Energy Management," and this is for the spring 2019 semester of Cyber-Physical System Security. I'd like to start off by giving some acknowledgments to the people who created this paper. The authors are Adrian Tang, Simhat Sethamad-Havan, Salvatore Stovo, and I apologize if I butcher those names, and they are with Columbia University. This paper was presented at the 26th USENIX Security Symposium in Vancouver, Canada, August 16th to the 18th. I've provided a link below. I'll start by giving some background. This is a hardware-software energy management mechanism, and they are used extensively in modern devices to optimize energy use. An example would be a software-controlled fine-tuning of the frequency and voltage provided to improve battery life. Introducing the vulnerability, the clkscrew attack, which is a new class of fault attacks aimed at these energy management mechanisms. There's no need for physical access to the device. A malicious kernel drivers use to extract secret cryptographic keys from trust zones, and it is able to escalate its own privileges. It's highly vulnerable due to security-oblivious designs. The clkscrew attack is more powerful than physical vulnerabilities for the following reasons. Unlike physical fault attacks, clkscrew enables fault attacks to be conducted purely with software. Remote exploitation is possible with no need for physical access. Equipment-related barriers such as soldering to achieve physical fault attacks are not needed as well. Physical attacks have been around a lot longer and therefore have several defenses in place already, such as special hardened epoxies and hard-to-access circuit chips. In other words, we're used to physical attacks, but these new software vulnerabilities are much more dangerous. To continue giving some more background, the energy management is an essential feature of most devices today. It performs such crucial tasks as increasing battery life, improving portability, and reducing costs. Designing an effective solution in this space requires the coordination between hardware designers, system architects, and kernel and application developers. The complexity of hardware and software interoperability, along with the pressure of cost and time to market, make these mechanisms a source of security vulnerabilities and offer an attractive target to attackers. An example of a vulnerable system would be the dynamic voltage and frequency scaling mechanism, DVFS for short. DVFS is an energy management technique implemented to save energy. Works by regulating frequency and voltage of the processor cores according to runtime computing demands. So this happens in real time. At the hardware level, it must be portable across a wide range of devices. And at the software level, the kernel developers need to track and match program demands to operating frequency and voltage settings on the fly. Hardware and software functions need to cooperate at a very fine granularity. I'll continue to provide a little bit more background on DVFS. It debuted in 1994 and has become ubiquitous in almost all commodity devices. DVFS works by regulating two knobs that govern the amount of energy consumed in the system, frequency and voltage. This requires runtime task demands, which may vary drastically and quickly. In order to react to these changes quickly, DVFS requires components across layers in the system stack. This requirement for layer-specific feedback and low latencies drives the need for unfettered and software-level access to the frequency and voltage regulators. If configured incorrectly, these regulators could be set to values outside of safe operating levels. Good thing security was a top concern. About that. Let's talk a little bit about the DVFS attack vectors. The first one would be voltage regulators. These supply power to various components that are controlled by the Power Management Integrated Circuit, PMIC. SPM controls voltage supplies to the cores with a set of control registers, as shown on the right. privileged software like a kernel driver use these memory map control registers to direct voltage changes. An additional DVFS attack vector would be the frequency PLL-based regulators. PLL circuit generates an output clock signal of adjustable frequency. Output clock frequency may be controlled by changing the PLL multiplier. Similar to voltage, privileged software can initiate per-core frequency changes by writing to software-exposed memory-mapped PLL registers. So how can this become a problem? Well, there are many dangers: overclocking and undervolting. Incoming data signals have to be held stable for T setup during the receipt of a clock signal. Input signals have to be held stable for TFF within the flip-flop after the clock signal arrives. Minimum Tmax path for output to propagate an input requires a minimum clock cycle, T-clock in this equation below. If two consecutive rising edges are violated, the output fails to latch properly and time effectively causing the output to operate with stale data. Two situations accomplish this: overclocking, which reduces T-clock, and undervolting, which increases overall circuit propagation time. We have some time graphs on the right for you to examine. There are several difficulties in performing a clockscrew attack. First off, regulator operating limits. In some cases, the operating of the regulators are not wide enough to provide a way to damage the device. In other words, the device can take all available inputs. Self-containment within same device. Attack code and victim code are on the same device, so execution code must still be operational. Noisy, complex OS environments. Non-deterministic OSs have many interrupts. Code must run without causing issues with these. Precise timing. Precise timing of when the fault is induced is required, as we saw on the previous graph. Fine-grained timing resolution. Fault need to be transient enough to occur during the intended region of the victim code execution. These have to be carefully placed. Let's look into the specifics of attacking a device. In this example, we'll use the Nexus 6. Investigating the Nexus 6 definition file, we are able to obtain the table of valid voltage and frequency pairs. This is found readily online in the file apq8084.dtsi for the Nexus 6. Maintaining a nominal base frequency of 300 MHz, an attacker could increase the voltage to verify where the device remains functional. It turns out the Nexus 6 reboots or freezes outside the range of 0.6 volts to 1.7 volts. These ranges create an unstable environment. Next, we can test the frequency vulnerability. We can do this by increasing the frequency against steps of 5 millivolts change in the voltage range until we get a similar fault. This provides us a table of unstable frequency and voltage ranges for this device. It is evident the hardware regulators can be configured past the intended limits for the Nexus 6. This is a powerful way to induce a software-based fault. We will continue investigating attacking the Nexus 6. With no safeguard limits for frequency and/or voltages, the device is quite vulnerable. Many options for attack. Reducing the operating voltage lowers the minimum required frequency needed to induce faults. Voltage and frequency limits must be enforced in tandem to prevent this vulnerability. On the right is a graph of timing, and we can see that it's a tight fit. Let's continue examining what a successful attack on the Nexus 6 would need. There are still more challenges to make this attack successful. As mentioned before, fault injection attacks must not induce errors to specific victim code execution. Custom kernel driver must be launched separate threads for attack and victim code to pin each in separate cores to prevent this. This is possible due to the deployment of processors like ARM, Intel PCPS, and Qualcomm ASIMP, which use separate frequency and voltage domains across different cores. The Nexus 6 implements the ASMP architecture, which with core pinning can manipulate the frequency of the core that the victim code executes while leaving the core of the attack code untouched. Disabling interrupts assures no context switch occurs between the cores. These two measures ensure the attack code is contained within the core the target victim code is running on. Essentially, the isolation of the voltage and frequency domains makes a cross-core fault attack possible. Next, let's discuss the steps that are needed for a clockscrew attack to work. The clockscrew attack is implemented with a kernel driver to attack code that is executing at a higher privilege than the kernel. Examples of victim code are applications running with isolation technologies. Some of these would include ARM Trust Zone and Intel SGX. These are used across many platforms. The figure in this slide illustrates the key attack steps within the thread execution of attack and victim code. The goal of the clockscrew attack is to induce a fault in a subset of an entire victim thread execution. As seen in this graph, the timing needs to be extremely precise. The clockscrew attack steps are continued by clearing residual states. So before attacking the victim code, we must make sure there are no microarchitectural residual states, that's actually a word, I looked it up, remaining from prior execution. To do so, we invoke both the victim and attack threads in two cores multiple times in quick succession. Experiments have shown that 5 to 10 iterations of this will suffice. Next, we must profile for an anchor. Since victim code is typically a subset of the entire victim thread execution, we must profile the execution of the victim thread to identify a consistent point of execution just before the target code is to be faulted. This is referred to as a timing anchor. T-anchor is the symbol used, which guides when to deliver the fault injection. Instruction or data profiling techniques may be used to accomplish this. Continuing on the clockscrew attack steps. Pre-fault delaying. Even with timing anchor, there may still be a need to fine-tune the exact delivery timing of the fault. The attack thread may be configured to spin loop with a predetermined number of loops before inducing the actual fault. This is essentially a technique to induce timing delays with high precision. This delay is indicated as FP delay. Next, we deliver the fault. Given a base operating voltage, F volt, the attack thread will raise frequency of the victim core, keep that frequency for the F duration loops, and then restore the frequency. To summarize the clockscrew attack steps, given a victim code and a fault injection target point determined by T-anchor, the attacker has to find optimal values for the following parameters to maximize the odds of inducing the desired fault. Fault injection parameters are shown below. F volt is the base operating voltage. FP delay indicates the number of loops to delay/wait before the fault. F frequency high is the target value to raise the frequency to for the fault. F frequency low indicates base value to raise the frequency from for the fault. And F duration is the duration of the fault in terms of number of loops. As alluded to throughout this presentation, this vulnerability is applicable to other platforms. The highlighted attack enablers in preceding sections apply to other leading architectures. The entire industry is increasingly moving to fine-grained energy management designs that separate voltage and frequency domains for the cores. For example, Intel. Intel's recent processors are designed with the base clock separated from the other clock domains for additional scope of energy consumption optimization. This design would be vulnerable to overclocking on Intel processors. Intel has made progress with the emergence of the Secure Enclave SGX. A closer look at the security guarantees would be needed to understand effectiveness of these hardening strategies. Other applicable platforms include ARM version 8. These devices adopt the ARM big.little design, which implements non-symmetric cores in the same system. Since these cores are of different architectures, they exhibit different energy consumption characteristics. It is thus required they have separate voltage and frequency domains. This strategy exposes devices to similar potential dangers from the software-exposed energy management mechanisms. It's not only phones, though. Cloud computing providers. The need to improve energy consumption does not just apply to user devices, but extends to cloud computing providers. Since 2015, Amazon AWS offers EC2 VM instances where power management controls are exposed within the virtualized environments. This allows users to fine-tune the processor's performance using P-state and C-state controls. Further research to assess the security ramifications of such user-exposed energy management controls in cloud environments is needed. So let's next discuss hardware, the defenses that we could implement, and the challenges associated with each defense. Operating limits in hardware. We could set hard limits that would need to be enforced with the regulators in the form of additional limit checking logic, or eFuses. This is very challenging, as these circuits are used in many models, and a one-size-fits-all may not be obtainable in a cost-driven environment where post-manufacturing processes are extremely expensive. Next, we could look at separate cross-boundary regulators. Maintaining separate regulators physically while operating execution mode switches is very expensive, though. DVFS typically span across system stack. Implementing this would cost precious runtime performance of trusted code and increase complexity. Lastly, we could try redundancy, checks, and randomization. This would require a complete redesign of the application core chip with additional logic and timing redundancy in addition to recovery mechanisms. This would also be very expensive. Adding reconfigurable hardware may be an option here as well, but again, this would be part of a complete redesign. Next, let's look at the software and its defenses and challenges. You could try randomization, introducing randomization to the runtime environment, but this will only offer limited protection against attacks that implement runtime profiling. Basically, there's ways around this. Redundancy and checks. Checksum integrity verification and execution redundancy are useful in high dependability systems, but are not typically deployed on commodity devices like phones because they impact energy efficiency. There's an awful lot of phones out there. So in conclusion, let's talk about some lessons learned. This is a very real vulnerability in many devices. Security needs to be considered at all stages of development. Solving this problem up front would have been a lot easier than implementing a fix at the end. As we saw, many of the potential solutions have serious challenges associated with themselves as well. Design decisions that contribute to the success of the attack are supported by practical engineering concerns. However, a coordinated full system response should be used to prevent these types of catastrophic vulnerabilities and could be done for a modest cost increase, and it would increase the ability to harden energy management systems. Better verification and validation methods, along with working with security researchers, will provide more robust systems for the future. I'd like to once again clearly note that this is based on a paper, and these are the sources. To be clear, I'm reporting on research and using diagrams in this presentation provided by others. List their names again as the authors from Columbia University. And once again, it was presented at the 26th USNIC Security Symposium in Canada. And once again, here's a link to the original paper.